future impact, scalability, and conclusion. Now, let's look toward the future. Our solution not only addresses lunar waste management but also offers adaptable, sustainable recycling technologies that can be applied here on Earth. This transformative approach paves the way for closed-loop, zero-waste recycling systems capable of supporting both extraterrestrial habitats and terrestrial circular economies. In the long term, our zero divided by zero systems will revolutionize resource recovery by enabling scalability. Our modular design means that the system can be expanded or adapted to meet the needs of different missions, whether it's for a small lunar settlement or large-scale Earth-based recycling facilities. Adaptability. The core technologies, advanced recycling, digital twin simulations, and AI-driven process optimization can be tailored for various environments, ensuring efficient operation under extreme conditions, from the lunar surface to urban industrial settings. Sustainability. By achieving nearly 100% material recovery and converting waste into valuable feedstocks and energy, our system reduces dependency on external resources and minimizes environmental impact. Looking ahead, we are actively pursuing strategic partnerships with academic institutions, industry leaders, and government agencies. For instance, our collaboration with the University of Alabama will not only strengthen our research capabilities but also open up extended research opportunities, providing a robust platform for further innovation. These partnerships will drive the continuous improvement of our recycling processes and support large-scale pilot projects on Earth, fostering sustainable practices that benefit communities and ecosystems. Moreover, our solution has significant implications for both space exploration and Earth's environment. In space, it will enable self-sustaining habitats that reduce logistical constraints and support long-duration missions. On Earth, the technology can be adapted to manage municipal and industrial waste more effectively, promote energy efficiency, and create resilient, circular economies that conserve resources for future generations. As we conclude, I want to reiterate that our zero-zero systems represent more than just a recycling solution. They embody a paradigm shift in how we view resource recovery and sustainability. By turning every fraction of waste into a valuable resource, we are setting the stage for a future where human ingenuity meets environmental stewardship in a truly transformative way. I invite you to join us on this journey towards sustainable innovation. Together, we can redefine the future of waste management, both in space and on Earth. Thank you for your time and attention. Development planning and risk management. Now, I will outline our comprehensive development plan for Phase 2, detail the steps required to transform our concept into a fully functional prototype, and discuss our risk management strategy along with our preliminary budget and funding sources. On screen, you'll see a Gantt chart visualizing our overall timeline. Phase 1, Material Testing, months 1 to 6. During the first 6 months, our focus is on material testing and subsystem validation under simulated lunar conditions. Our key objectives are finalizing detailed CAD models and complete assembly drawings, conducting simulation analyses, finite element analysis, thermal modeling, to optimize design parameters, prototyping key subsystems, such as the bioreactor, thermal depolymerization reactor, and separation system, using Earth-based simulants. Testing these subsystems under controlled conditions that mimic lunar temperature, pressure, and vacuum. Visual cue, display a timeline chart showing milestones for CAD refinement, simulation benchmarks, and initial prototype tests. Our success criteria for Phase 1 include achieving recycling efficiency targets of 99% or greater, maintaining system reliability with at least 95% uptime, and validating energy recovery that confirms our closed-loop concept. Phase 2, Prototype Development, months 7 to 12. In Phase 2, we develop a fully integrated prototype. Our goals are fabricating custom components, advanced shredders, separation modules, and procuring off-the-shelf items, sensors, controllers. Integrating individual modules, pre-sorting, fragmentation, separation, conversion, and energy recovery into a cohesive system in a laboratory environment. Conducting rigorous tests under simulated lunar conditions, vacuum, extreme temperatures, to ensure system coherence. Optimizing interfaces between modules to ensure smooth material flow and maximal energy efficiency. Visual cue, use a detailed timeline graph with milestones for component fabrication, integration testing, and environmental validation. Success in Phase 2 will be measured by seamless module integration, full cycle test results meeting our efficiency targets, and effective real-time optimization via the digital twin. Phase 3, full system testing and lunar deployment, months 13 to 24. Phase 3 involves full system testing and preparing for potential lunar deployment. Assembling a field-ready prototype designed to operate in a simulated lunar environment. Conducting extended tests in thermal vacuum chambers to simulate lunar conditions and monitor full-cycle performance over prolonged periods. Documenting performance data, including recycling efficiency, energy balance, and system uptime, and refining our design accordingly. Developing a deployment strategy that outlines logistics, integration with lunar habitats, and operational plans. Visual cue, present a Gantt chart illustrating Phase 3 milestones, including prototype assembly, field testing, and final design adjustments. Success in Phase 3 is defined by consistently achieving 100% net waste recycling, maintaining over 95% operational uptime, and developing a comprehensive deployment plan that meets Lunar mission criteria. Risk assessment and mitigation. We have identified key risks along with mitigation strategies. Thermal failure in reactors, high-use advanced heat-resistant materials, and optimized cooling systems. Energy inefficiency, medium-optimized solar arrays, incorporate redundant energy storage, and apply adaptive control algorithms. Integration of advanced modules, high-conduct thorough interface reviews, use standardized modular interfaces, and perform incremental integration tests. Component fabrication delays, medium partner with multiple suppliers, include contingency time, and employ rapid prototyping. System reliability under extreme conditions, medium utilize thermal vacuum chambers for testing and simulate conditions using our digital twin. Crew interface and safety, medium develop comprehensive SOPs, implement remote monitoring, and conduct regular training drills. Budget overruns, medium allocate a contingency budget of 15 to 20% and secure additional funding through partnerships and grants. Visual cue, display a risk assessment table summarizing each risk, its level, and the corresponding mitigation strategy. Preliminary budget and funding sources. Our preliminary budget for Phase 2 is estimated at $1,600,000, broken down as follows. Detailed engineering and CAD refinement, $150,000. Component fabrication and procurement, $500,000. Subsystem integration and laboratory assembly, $300,000. Testing and validation, $250,000. Personnel and training, $200,000. Contingency, 15 to 20%, $200,000. Funding will come from a combination of our Phase 1 prize purse, partner contributions, strategic academic partnerships, and external grants. Visual cue, display a detailed budget table along with a pie chart illustrating cost distribution, overlaid with financial milestones from the timeline. In summary, our structured development plan, comprehensive risk management, and well-defined budget ensure that our project is both feasible and sustainable. We are confident that our approach will lead to a fully operational lunar recycling system, paving the way for sustainable extraterrestrial operations. Let's shift our focus to the physical backbone of our system, the hardware and components. In this segment, I will present our preliminary CAD models, highlight key dimensions and design features, and walk you through our comprehensive equipment list. Every component is meticulously engineered to uphold our zero divided by zero principle of zero waste and full resource recovery. Our CAD models provide an assembly-level view of the entire recycling system. They clearly show the spatial arrangement of our major modules, the pre-sorting and identification unit, fragmentation and shredding module, separation and purification module, conversion and manufacturing module, energy recovery module, and the digital twin and control system. For example, the pre-sorting unit occupies an envelope of approximately 1.2 million cubic centimeters. Its precise dimensions allow optimal sensor placement and efficient waste intake. On screen, you'll see both isometric and sectional views that highlight key dimensions, height, width, and depth, as well as access panels and mounting interfaces, which are essential for maintenance and seamless integration. Now, let's review our equipment list by detailing each major component. The pre-sorting unit automates waste intake and material identification using advanced sensors such as XRF and Raman spectrometers, along with high-resolution vision systems. It has an approximate mass of 150 kilograms and a volume of about 1,200,000 cubic centimeters, operating within 0 degrees Celsius to 50 degrees Celsius and 90 to 110 kilopascals. This unit is calibrated for 100% reprocessing of incoming waste, which is crucial for maintaining our closed-loop system. The fragmentation and shredding module is responsible for reducing waste to uniform fragments. It utilizes high-torque shredders equipped with carbide-tipped blades and vibratory screens to classify particles by size. This module weighs around 200 kilograms, occupies roughly 1,800,000 cubic centimeters, and operates between 0 degrees Celsius and 60 degrees Celsius at 90 to 110 kilopascals. It provides a consistent particle size that enhances efficiency in subsequent processing stages. The separation and purification module isolates various materials using magnetic separators, centrifugal systems, and multi-stage filtration. With a mass of approximately 300 kilograms and a volume of about 2,500,000 cubic centimeters, it operates within 0 degrees Celsius to 50 degrees Celsius and 90 to 110 kilopascals. Its advanced purification processes ensure that any residuals are recycled back into the process, supporting full resource recovery. Next, the conversion and manufacturing module transforms sorted waste into recycled pellets, ingots, or other feedstocks through processes such as extrusion, pyrolysis, and electrorefining. This module weighs around 350 kilograms and occupies about 2,800,000 cubic centimeters. Its external housing operates between 0 degrees Celsius to 50 degrees Celsius, while internal processing zones can reach up to 500 degrees Celsius, managed by integrated cooling and insulation. It is configured to achieve near-zero byproduct loss, effectively closing the material recovery loop. The energy recovery module captures residual thermal and chemical energy from byproducts and converts it into electrical power. It has an approximate mass of 250 kilograms, a volume of 1,500,000 cubic centimeters, and operates at 0 degrees Celsius to 50 degrees Celsius under 90 to 110 kilopascals. By reusing waste energy to sustain continuous operation, it plays a critical role in our self-sustaining system. Our digital twin and control system is the nerve center that provides real-time monitoring and adaptive control through AI-driven optimization. With a mass of around 100 kilograms and a volume of about 800,000 cubic centimeters, this system operates within 0 degrees Celsius to 50 degrees Celsius and 90 to 110 kilopascals. It dynamically adjusts processing parameters to ensure maximum efficiency across all modules. Finally, the auxiliary systems, which include conveyors, safety enclosures, sensor mounts, and access panels, support material handling and facilitate maintenance. These systems weigh approximately 150 kilograms and occupy about 1 million cubic centimeters, operating under the same environmental conditions as the rest of the system. They enable easy modular integration and ensure that maintenance can be performed quickly, keeping the overall system operating seamlessly. Each component in our system is engineered to embody the 0 divided by 0 principle. This means that every fraction of waste, even the smallest residue, is captured and reprocessed. Our design ensures complete material recovery and converts residual energy into usable power through the energy recovery module. Moreover, all modules are interconnected through our digital twin control system, which continuously monitors and dynamically adjusts operating parameters to maintain optimal efficiency. On screen, an integrated schematic shows how outputs from one module feed into the next, reinforcing the closed-loop, zero-waste concept. In summary, our detailed CAD models, comprehensive equipment specifications, and modular design collectively ensure that every component supports our 0/0 system, where no resource is wasted. This robust hardware foundation is essential for creating a sustainable, self-sufficient lunar habitat. Thank you. Introduction to hardware and components. Now, let's shift our focus to the physical backbone of our system, the hardware and components. In this segment, I will present our preliminary CAD models, highlight key dimensions and design features, and walk you through our comprehensive equipment list. Each component is meticulously designed to adhere to the 0 divided by 0 principle of zero waste and full resource recovery. Visual cue: display an overview slide with a high-level CAD rendering showing the full layout of the recycling system within the habitat module. Preliminary CAD models and key dimensions. Our CAD models provide an assembly-level view of the entire system. These models illustrate the spatial arrangement of our major modules. Pre-sorting and identification unit. Fragmentation and shredding module. Separation and purification module. Conversion and manufacturing module. Energy recovery module. Digital twin and control system. Each module is designed with precise dimensions to optimize space utilization and ensure smooth integration. For instance, the pre-sorting unit occupies an envelope of approximately 1.2 million cubic centimeters, with critical dimensions that allow for effective sensor placement and waste intake. On screen, you will see both isometric and sectional views highlighting height, width, and depth, as well as access panels and mounting interfaces that facilitate maintenance and integration. Visual cue: show detailed CAD drawings with annotated dimensions and key integration points. Walkthrough of the equipment list. Let's now review our equipment list, where we detail each major component's function, mass, volume, operating conditions, and integration features. Pre-sorting unit. Function: automates waste intake and material identification using sensors, XRF, Raman, and vision systems. Mass: approximately 150 kilograms. Volume: about 1,200,000 cubic centimeters. Operating conditions: designed to operate within 0 degrees Celsius to 50 degrees Celsius and 90 to 110 kilopascals, fitting the controlled habitat environment. Integration: calibrated to reprocess 100% of incoming waste, which is crucial for maintaining our closed-loop 0 divided by 0 system. Fragmentation and shredding module. Function: reduces waste to uniform particle sizes using high-torque shredders with carbide-tipped blades and vibratory screens. Mass: approximately 200 kilograms. Volume: around 1,800,000 cubic centimeters. Operating conditions: operates between 0 degrees Celsius and 60 degrees Celsius at 90 to 110 kilopascals, ensuring robust performance under varying conditions. Integration provides consistent particle size, maximizing efficiency in downstream processes. Separation and purification module. Function isolates different materials using magnetic separators, centrifugal systems, and multi-stage filtration. Mass, approximately 300 kilograms. Volume, about 2,500,000 cubic centimeters. Operating conditions, maintains a temperature range of 0 degrees Celsius to 50 degrees Celsius and a pressure of 90 to 110 kilopascals. Integration, advanced purification reintroduces residuals back into the process, supporting full resource recovery. Conversion and manufacturing module. Function, transforms sorted waste into recycled pellets, ingots, or other feedstocks through processes such as extrusion, pyrolysis, and electrorefining. Mass, approximately 350 kilograms. Volume, about 2,800,000 cubic centimeters. Operating conditions, the external housing operates between 0 degrees Celsius and 50 degrees Celsius. Internal processing zones can reach up to 500 degrees Celsius with localized cooling and insulation. Integration, configured for near-zero byproduct loss, ensuring every output is reprocessed. Energy recovery module. Function, captures residual thermal and chemical energy from processed byproducts and converts it to electrical power. Mass, approximately 250 kilograms. Volume, around 1,500,000 cubic centimeters. Operating conditions, operates within 0 degrees Celsius to 50 degrees Celsius at 90 to 110 kilopascals. Integration, reuses waste energy to support continuous operation, essential for a self-sustaining system. Digital twin and control system. Function, provides real-time monitoring and adaptive control via AI-driven optimization. Mass, approximately 100 kilograms. Volume, about 800,000 cubic centimeters. Operating conditions, designed for 0 degrees Celsius to 50 degrees Celsius and 90 to 110 kilopascals. Integration, ensures continuous adaptation of processing parameters to maintain efficiency. Auxiliary systems. Function, includes conveyors, safety enclosures, sensor mounts, and access panels to support material handling and maintenance. Mass, approximately 150 kilograms. Volume, around 1 million cubic centimeters. Operating conditions, operates within 0 degrees Celsius to 50 degrees Celsius and 90 to 110 kilopascals. Integration, facilitates modular integration and quick maintenance, ensuring overall system continuity. Visual cue, display a table summarizing each component, with columns for function, mass, volume, operating temperature, operating pressure, and key integration features. Highlight annotations that emphasize adherence to the 0/0 principle. Emphasizing the 0 divided by 0 principle. Every component in our system is designed with the 0 divided by 0 principle in mind, ensuring zero waste and full resource recovery. Our design ensures that every fraction of material, even the smallest residue, is captured and reprocessed. The energy recovery module converts residual heat and chemical energy back into usable power. All modules are interconnected through our digital twin system, which dynamically monitors and adjusts operating conditions to optimize resource recovery. On screen, you can see an integrated schematic that illustrates the flow between modules. Arrows indicate how outputs from one module become inputs for another, with clear labels showing where energy recovery and material recycling occur. Visual cue, present an integrated diagram highlighting module interconnections and the closed-loop flow of materials and energy. In summary, our hardware and components are engineered for maximum efficiency, reliability, and adaptability under lunar conditions. The detailed CAD models, comprehensive equipment specifications, and modular design not only maximize material recovery but also embody our 0 divided by 0 philosophy, ensuring every bit of waste is repurposed. This approach is critical to creating a sustainable, self-sustaining lunar habitat. Thank you. Visual cue, conclude with a final slide summarizing key hardware metrics, accompanied by an animation looping through the interconnected modules to reinforce the concept of a fully integrated, zero-waste system. Introduction to the production cycle. Now, let me guide you through our full production cycle, a step-by-step overview of how our integrated recycling system transforms lunar waste into valuable resources. This cycle is designed for maximum efficiency and minimal crew intervention, operating continuously with real-time monitoring via our digital twin dashboard. On screen, you'll see a high-level flowchart outlining the 5 key stages of our process. Step 1, waste intake and pre-sorting, 10-minute segment in process cycle. In the first stage, waste intake and pre-sorting, our system begins with a robotic arm delivering the waste into the pre-sorting and identification unit. Here, a network of sensors, including XRF and Raman spectrometers, and high-resolution vision systems, rapidly analyzes and categorizes each item by its material type and contamination level. Visuals on screen display a close-up animation of waste entering the system, being scanned, and sorted into designated bins. This stage, which represents a 10-minute segment in our processing cycle, ensures that every piece of waste is accurately identified and routed for subsequent processing. Step 2. Fragmentation and shredding, 15-minute segment. Next, the sorted waste moves into the fragmentation and shredding module. Here, heavy-duty, high-torque shredders equipped with carbide-tipped blades break down the waste into uniform fragments. Vibratory screens immediately follow, classifying these fragments by particle size to ensure a consistent feed for downstream processing. An animated sequence illustrates the shredders in action, showing large waste pieces being reduced into smaller, uniformly sized particles, which then flow onto vibratory screens. This stage is allocated a 15-minute segment in the cycle, setting the stage for efficient separation of materials. 13:45 to 14:30, Step 3, Separation and Purification, 15-minute segment. Following shredding, the material enters the separation and purification module. In this stage, a series of magnetic, centrifugal, and filtration systems work in tandem to isolate the different materials, such as plastics, textiles, metals, and composites. Magnetic separators attract ferrous metals, while centrifugal systems separate materials based on density. Multi-stage filtration removes any residual impurities. On screen, a multi-panel animation shows each separation process simultaneously, particles being pulled by magnets, denser fragments settling through centrifugal force, and fine impurities being filtered out. This step also occupies a 15-minute segment, ensuring the purity of the separated streams before they enter the conversion process. Step 4, Conversion and Manufacturing, 20-minute segment. At the heart of our production cycle is the conversion and manufacturing module. Here, each waste stream undergoes tailored conversion processes. For plastics, the waste is melted and repolymerized via controlled extrusion and pyrolysis, producing recycled polymer pellets. For textiles, hydrothermal processes, possibly combined with enzymatic treatment, recover fibers which are then reconstituted into new materials. For metals, electrorefining and thermal treatments purify metal scrap into high-quality ingots. For composites, mechanical and thermal methods separate composite materials into fibers and resin fractions. A series of detailed animations and process flow diagrams illustrate these conversion steps. Visuals highlight temperature profiles, pressure conditions, and real-time process adjustments as our digital twin system monitors and optimizes operations. Step 5. Finishing and Output Collection. Finally, in the finishing and output collection stage, the processed materials are collected and sorted. The outputs, recycled polymer pellets, reprocessed fibers, metal ingots, and composite feedstocks, are then directed to storage areas or prepared for direct application in manufacturing new components for the lunar habitat. The animation on screen demonstrates the organized flow of outputs from the conversion module into storage or assembly lines. This stage is allocated a 10-minute segment, completing the full production cycle. Cycle overview, daily throughput, and crew involvement. To summarize, each full production cycle takes approximately 1 hour. Given our design, we estimate a daily throughput of /begin, itemize, /item 500 kilograms of plastics, /item 150 kilograms of textiles, /item 200 kilograms of metals, /item 100 kilograms of composites. /n, itemize, this allows for 8 to 10 complete cycles per day. Our system is designed for minimal crew involvement. Routine operations, such as waste loading and system monitoring, are managed remotely via our digital twin dashboards, ensuring that only essential manual interventions, such as periodic inspections or maintenance, are required. Typically, only 1 to 2 crew members are needed per 8-hour shift, dedicating about 1 to 2 hours per shift to operational supervision and an additional 1 to 2 hours to maintenance. In conclusion, our concept of operations is engineered to be efficient, fully automated, and scalable. The integration of precise waste sorting, uniform fragmentation, efficient separation, tailored conversion processes, and organized output collection creates a robust, continuous production cycle. This cycle not only achieves near 100% recycling efficiency but also minimizes resource usage and crew involvement, making it ideally suited for sustainable lunar habitation. Introduction to Integrated Recycling Modules. Now, let's explore the integrated recycling modules that form the backbone of our system. Each module is designed to operate autonomously yet in synergy with the others, ensuring that every fraction of lunar waste is efficiently processed into usable materials. I will walk you through each module, highlighting its key functions, components, and how they interact within the closed-loop system. On screen, you'll see detailed CAD renderings and animations that illustrate these interactions. Pre-sorting and Identification Unit. First, the pre-sorting and identification unit is our system's entry point for waste. This module performs the crucial task of accurately categorizing incoming waste. It is equipped with an array of high-precision sensors, including X-ray fluorescence, XRF, spectrometers, to analyze elemental composition, Raman spectrometers, for identifying molecular structures, vision systems, utilizing high-resolution cameras and advanced image recognition software to visually classify materials. This unit employs a conveyor-based or robotic intake mechanism that directs waste into designated bins based on its type and contamination level. The system is calibrated to ensure even the smallest fractions of waste are detected and sorted. As you watch the animation on screen, notice how sensor data is integrated in real time into our digital twin model, enabling immediate feedback and dynamic adjustments to the sorting process. This ensures that our downstream processes receive clean, well-categorized material, which is critical for achieving near 100% recycling efficiency. Fragmentation and Shredding Module. Once sorted, the waste enters the Fragmentation and Shredding Module. This module's primary objective is to reduce waste into uniform fragments, which greatly enhances the efficiency of subsequent separation and conversion steps. Key components include high-torque shredders. These are equipped with carbide-tipped blades designed to handle a variety of materials, from tough plastics to fibrous textiles, ensuring thorough breakdown. Vibratory screens. After shredding, vibratory screens classify the resulting particles by size, sorting them into uniform batches. The shredding module is designed to handle a high throughput while maintaining consistency in particle size distribution. This uniformity is vital for the next stage, as it allows magnetic and centrifugal separators to work more effectively. In the accompanying CAD animation, you'll see how waste is fed into the shredders and then sorted by the screens, creating a steady, manageable stream of fragments that feed directly into the separation module. Separation and Purification Module. Following fragmentation, the next stage is the Separation and Purification Module. This module isolates the various material components through several integrated methods. Magnetic separators. These are used to extract ferrous metals from a waste stream. Centrifugal separators, designed to separate materials based on density differences, particularly effective for distinguishing metals from lighter polymers and textiles. Filtration systems. Multi-stage filters and specialized screens further purify the separated materials, removing any residual contaminants. Each of these systems works in parallel to ensure that every type of waste, whether plastics, textiles, metals, or composites, is isolated with high purity. The CAD rendering displayed shows a side view of the module, where you can see how the magnetic field and centrifugal force are applied. Visual animations illustrate how sorted fragments flow through the system, with distinct lanes for each material. Now, let's move to the Conversion and Manufacturing module, where the sorted materials are transformed into usable feedstocks or final products. This module incorporates several advanced conversion processes. Extrusion lines, for processing plastics, where waste is melted and reformed into high-quality recycled pellets ideal for injection molding or additive manufacturing. Pyrolysis reactors. These operate in a controlled vacuum environment, breaking down polymers into monomers and converting organic residues into syngas and biochar. Detailed animations on screen demonstrate the reactor's thermal profile and the controlled environment that minimizes toxic emissions. Enzymatic/mechanical fiber processing units, used for textiles. These units employ hydrothermal and enzymatic processes to recover natural fibers and separate synthetic polymers. Electrorefining cells, for metals. These cells purify scrap metal into high-grade ingots suitable for structural applications. Thermal/mechanical recovery systems for composites. These systems separate composite materials into their constituent fibers and resin fractions. A series of diagrams illustrates the flow from raw waste to finished product, emphasizing how each conversion process is fine-tuned to reclaim maximum material while conserving energy. The animation synchronizes with our digital twin data, demonstrating real-time process adjustments. Control and Digital Twin System. Finally, the Control and Digital Twin System serves as the nerve center of our integrated recycling modules. This system provides real-time monitoring. Sensors embedded throughout each module feed data into a centralized dashboard. Adaptive AI algorithms. These algorithms analyze performance data and adjust process parameters on the fly, ensuring optimal efficiency. Predictive maintenance. By simulating system behavior, the digital twin identifies potential issues before they occur, allowing for proactive maintenance. This digital layer is crucial for maintaining the closed-loop operation and achieving the 0/0 principle of zero waste. On screen, you'll see an animation of the digital twin interface, which displays live metrics from each module and highlights how the system responds dynamically to changing conditions. This integration ensures that even when faced with variable input conditions, our recycling process remains efficient, reliable, and fully autonomous. In summary, our integrated recycling modules, ranging from pre-sorting to real-time digital control, form a cohesive system that transforms lunar waste into valuable resources. Each module is carefully engineered to work in harmony, ensuring maximum material recovery and energy efficiency. This robust design is critical for sustaining life on the moon and paves the way for advanced, scalable recycling solutions both in space and on Earth. Composites are processed through a combination of mechanical and thermal techniques. In this stage, composite materials are separated into their constituent fibers